So part 2. In the first video, it was about us. So we are at chapter 3. We had video 1, which introduced us crystal structures. So in this video, I will start with point coordinates. What are point coordinates? The point coordinates defines the position of each atoms in a unit cell. To start, first I have taken this BCC crystal structure and I will write point coordinates for all of its atoms. First, I need to define axis system. So let's say this is X. It's up to us to choose whichever we want, Y and Z. This will be origin. For my origin, let's say X, Y, Z. Like this. And let me number these atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9 atoms in total. So what will be point coordinates for this one at the origin? It will be 0, 0, 0, isn't it? And let me remind you, we will always assume that the distance between these two atoms is equal to 1. So the sides of unit cells change between 0 and 1. So this is 0, this will be 1. If it is 0, this will be 1, and the same for z-axis. So for it was first 1 and 2. For atom number 2, point coordinates will be, its x coordinate will be 1, so 0 will move in x direction, 1. It doesn't have a y coordinate, it will be 0 and z will be 0. For number 3 over here, it will be, so how we can, let's say like this, I am at the origin, how I can move to this atom 3. If I move 1 in x direction and 1 in y direction, I am there. So it will be 1, 1, 0. For 3. For atom 4, x will be 0, y will be 1, z will be 0. For 5, this atom, it is right at the middle, so how we can go there? If I move half at x direction, half at y direction, half at z direction, so it will be 1 over 2, 1 over 2, and 1 over 2. For 6 over here, so if I move 1 in x direction, 1 in z direction, so 1, 1, 0. For number 7, which is this one, it will be, let's say, 1, 1, 1, 1, 1, 1. For 8, so in order to go from origin to number 8, I need to move 1 in y direction, 1 in z direction, 0, 1, 1. And the last one, 9, in order to go here, I am here. If I just move in z direction, full length, it will be 0, 0, 1. So that's the point coordinates of all atoms in BCC unit cell. And I assume you can solve the same thing for FCC. Just try it for yourself. Let's continue. Crystallographic directions. Here you see this blue direction and this red direction over here. Let me make first thing clear that this is not a vector, not a vector. It is a direction. Why? Here what's important for us is what's the direction. The length, the usual vector has a direction and length. Here, length for us, when we are working with directions, we only need to know what direction is this. We don't care about the length. So this vector will be equal to this in material science because we have infinite amount of cubes. So what we require to find is which point does it take us, not the length. Let's see the procedure. What we need to do is we have a direction over here and we should have some numbers to represent it. And because it's indices, Miller indices, and this Miller indices represents that vector. So let's try to find out what Miller indices represents that blue vector over here. The first way to find it, that we can do it one by one over here. First thing to do, if vector is not at the origin, bring it to the origin. So if it is here, just reposition it, start from the origin. The second part, read projections to x, y, and z axis. So I do it in this way. I am at the origin. How I can go from this origin to this part. So if I move again, this is 0, this is 1, this is 0, it is 1, 0, 1. So full length is 1. So I'm here. If I move positive x on positive x-axis, full length, and if I move up half length, 0.5, I will be there. So it means x, y, z. X was positive 1, y it was 0. I did not need it. For z it was positive 0.5. So third step is we need to make it integer. We can't have this 0.5 over here, so that's why we will multiply it by 2. So it will be 0, 2, 0, 1. The last step, to have a brackets around it, we don't use any kind of a comma, we don't use it. So 0, 2, 0, 1 is Miller indices that represents that blue vector over here. Let's try to do this red one over here. I will do it here, x, y, z. So we are at this point. Let me change the color. The height can go from this start to this end. So if I move, I will not go x, y, z. So I will start with y direction. So if I move positive y, in positive y, full length, if I go back in negative x, full length, and if I go up in z direction, again, full length. So what I have, positive y, full length 1, negative 1, and positive 1. It is an integer values. I don't need to make a change, just enclose it in a bracket, so it will be 1, 1, 1. To show this negative sign, we will add this cap above it. So this means negative 1. So that is the end. Let's continue. That's one way to do it. Let's try to solve some examples. Now we will deal one by one, A, B, C, D over here. Let's start from A. For A, as you see, this vector does not pass from the origin, so I have to reposition it to pass from the origin from here, or I can make some cheating. Let's say, instead of drawing it again, I can change the origin, the same thing. So I will choose this point as an origin. I have this y here, z here, and x-axis over here. So if it's my origin, how I can go from here to here, x, y, z. So we are here. If I move down, negative z, and it's full length, negative 1 in z-axis. If I go left, this side will be negative y, so positive y, this will be negative y. If I go full length in negative y, and I don't need x-axis, so it will be 0, negative 1, negative 1, enclose it in bracket, no commas. So that is Miller indices for vector A. For vector B, let's try now solve this one. So if I can choose this part as an origin, x, y, z directions will be the same. So how I can go from this start to this end over here? If I move, let's say this will be half length in y-axis, it will be positive 0.5. And if I move full length, negative x-axis, it will be negative 1. And as you can see, I don't need z direction. So x, y, z. X is negative 1, it is positive 0.5 and 0. So multiplied by 2 to get rid of this 0.5, it will be negative 2, 1, 0, and enclose it in a bracket. So if it is difficult for you to imagine this half length over here and change of origin, you can choose a second way to do it. So I will use this B in another way. If you remember in previous slide, we did point coordinates. We can do this. We have this start point coordinates and end point coordinates x, y, z. So what's the point coordinates of the start over here? It was start. We had to start here. Now this time I will assume that this is the origin. I'm not changing origin. So if you're uncomfortable with change of origin, you can use this way. So it's origin. Now what's point coordinates over here? It will be, actually let me erase all excess stuff to see things easier. I think that's enough. So what's point coordinates of the start here? If I move, let's say, full length in x-axis, so positive 1, half at y-axis, it's positive y, by the way, 0.5, and if I move full length, 1 in z-axis now, and I am there. What's the point coordinates of this end over here? This is origin. If I move positive y full length, is 1. Sorry, I didn't use x. So positive 1 in y-axis. So I was here. So move positive 1 in y-axis and up full length in z-axis. 1, 1, and I don't need x-axis. So start coordinates, end coordinates. So what you need to do is this end minus start. What it will be negative 1, 0.5, and 0. So 0.1 is negative 1, 1 minus 0.5, 0.5, and etc. Multiply by 2 to make an integer, negative 2, 1, 0, and enclose it in bracket. So you can choose either way to do it. Both are correct. Now let's move on. This time I will solve C and D. For C, I will use point coordinates. I guess this will be easier to explain. So this is start and end. Point coordinates of the start. It is half half. So half positive half in x, positive half in y. X, y, z. It was 0.5, 0.5 and Z is 0 because it's at the ground level. For this N over here, in order to go there, so if I go full length in positive X, full length in positive Y, full length in positive Z, I am there. For N, 1, 1, 1. So 1 minus 0.5, 1 minus 0.5, 1 minus 0, 1. Multiplied by 2, 1, 1, 2, and enclose it in a bracket. That's Miller indices for vector C. And now I will do this D vector over here. But first let me erase others. Let's choose some critical. Okay. We can start and X, Y, Z. The start is here. I have origin here. So what's coordinates? Half length in X, 0.5. Full length in Z, 1. So it will be 0.5. I didn't use Y. That means 0, 1. For N, which is here. If I go, let me change color. So if I go full length in X, half length in Y. So 1, 0.5, and I didn't use Z, 0. So end minus start, it will be 0.5, 0.5, negative 1. Multiply by 2, 1, 1, negative 2, and enclose it in a bracket without commas. That's the Miller indices for vector D. So in this slide, we have the direction. Actually, sorry, I was mentioning vector, but it's a direction, not a vector. What we did, the directions picture was given. We acquired indices for that direction. Now we will do the reverse. The Miller indices is given, and we are required to draw that direction. So as you see, X, Y, Z axis is not given, so it's up to you to choose whatever you like to make things easier. The first, I will do this one, and I will pick this one as positive Z, positive Y, and positive X-axis. This will be my origin. So what do we have? First, open the bracket, negative 1, negative 2, 1. Remember, I mentioned that this side of the unit cell changed between 0 and 1, and I have this 2 over here. So I can't have value bigger. So my value should be between negative 1 and positive 1. I can't have something bigger or smaller because I assume that this side will be length 1. That's why I will divide it by biggest value over here, which is 2. So I will divide this by 2. It will be negative 0.5, negative 1, negative positive 0.5. Now we can start to draw them. So this is positive X. I need to move half in negative X direction. So I guess it will be enough. So I'm moving negative X direction. Now I'm here. So now I need to move negative 1 in Y direction. Now I am moving to the left at this 1 proportion. Now I am here. This time I need to move 0.5 in positive Z direction. I guess this will be enough. And connect start with end point. It will start origin, and that's end point. That is the direction for this indices, Miller indices. Now this time, so what we did, open the bracket, make it so that you don't have any value bigger than 1 or smaller than -1. Choose axis system and start drawing. For the second one, let's do it over here. It is -1, 0, 3. I can't have something bigger than 1, so divide it by 3. It will be -1 over 3, 0, and 1. So this time I will change my axis system. I can see that I have this -x over here. I will choose this as -x axis, this as +z, this as positive. Let me actually do this. Okay, I want this one to be positive y. Okay, let's just have it in this way. So what do I have? For x direction, -1 over 3. It's my negative x direction. I am here at the origin. 1 over 3 part, I guess, will be this. So I am here. 0 in y direction, x, y, z. 0 in y direction, so I will not move. 1 in positive z direction. Connect start with the proper. And now this time I will connect start with end. And that's our vector. See the difference? I made it -x so that it will be inside the cube, so it may be easier to see how does it look like. It doesn't matter whatever you choose, because if you look at this picture over here, this vector goes outside of the cube. That means it is a part of another cube, which is at the left side. What I did over here, just imagine you rotate it in this way. It is an infinity. You can look at it either way you want it. Now that's our vector over here. Let's continue. So here we had cubic directions. First we had a picture of it and extracted some values, and in the second part we had values and we learned how to draw that direction. Now we are moving to hexagonal close-packed crystallographic directions. What's different over here? In cube, we have 3-axis system, x, y, z, but in hexagonal close-packed, we have 4-axis system, which is A1, A2, A3, and Z. And Z-axis, so note the positive directions. This is positive A1. It will be negative A1. Positive A2, it will be negative A2. Positive A3, this side will be negative A3. And again, it changed between 0 and 1. If it is 0, this is 1. 0, 1. 0, it will be negative 1. 0, positive 1, 0, negative 1, and this will be negative 1 over here. And we have z-axis over here, and it applies the same. If it is 0, this length will be 1. So we are taking actually proportions. It's 1 proportion. As you see, this side is longer than this, but we are taking both as equal to 1. Not exactly so. So what's the procedure? We understand this axis system. We have 4-axis system. It's called Miller-Bravais axis system. The first thing to do, we have this green vector over here, and it does not pass from the origin as you see. First thing you have to do is reposition it so that it passes from the origin. Let me erase something over here. Okay. So we will reposition this vector so that it passes through the origin. So it will be this. As you see, this green is equal to this red one, and also we can choose this vector over here. It will also be equal to this others. So I need this green one, red one over here. So I did this first step. I did reposition it. so that it will pass through the origin. So now we have to read the projections. But which projections? Now we have to extract the certain values. What's the projection on A1, A2? We will skip A3 and Z. So what we need to do, we have start, we have the end. We need to guess, find how we can go from this start to the end using only A1, A2 and Z axis. Forget A3. So let's see what we can do. We can either move on axis or parallel to it. So if I'm here, let me change the color. I'm here. If I move on A1 positive, so positive 1, now it can move this way. This line is parallel to A2. I can use it. So it is full length, by the way. So plus 1 over here. A2 is also plus 1. I don't need to use z-axis. So it is 0. So plus 1, 0. That's the projections of this direction on A1, A2, and z-axis. The third step, adjust the smallest integer values. As you can see, these are integers, so I don't need to have extra step. Step 4, convert 3 to 4 axis system. As you can see, I have 1 to 3 values, and we will use some formulas and convert it to 4 axis system. Actually, as you can see, I have written A1, A2, Z over here, but this values over here is not yet A1, A2, and Z. We will give them some temporal names. This one for now will be U dash, V dash, and W dash. After we plug it in equation and with the values, I will get A1, A2, and Z. Let's move on. So here I have the same vector over here. Let's move on. What was our projections? It was for A1, positive 1, positive 1. We didn't have A3 yet. And Z was 0. We don't need to adjust the integer values, not required for now. But don't forget to do the step. Now we will apply the equations. As you can see, this is U dash, V dash, W dash. For me it was 1, 1, 0. I will use this equation, so plug in 1 over here, 1, 1, 1 over here. So what will be our values? It will be 1 over 3. This one will also be 1 over 3. Now if you come here, it is negative U plus V. So this is U, not U dash. This is V, not V dash. So 1 over 3 plus 1 over 3 equals to negative 2 over 3. And Z, this W does not change. It will be 0. So what's my values? 1 over 3, 1 over 3, negative 2 over 3, and 0. So I need to adjust it to integer. So multiply by 3. It will be 1, 1, negative 2, 0. And close it in a bracket. 1, 1, negative 2, 0. And that's it. Let's continue. For this one, let's do the same procedure for this one. It passes from the origin. So I can skip step 1. So we need to read the projections on A1, A2, and Z. Forget A3 again. Or I can go from start to here. If I just move, this side is negative A2. Negative 1 on A2. Let me write down here. Negative 1. And if I move up, I guess it's half length. So move up in positive Z. So negative, positive 0.5. I did not use A2. It was not required. So it is 0. I need to adjust it to integer. Multiply by 2. It will be 0, negative 2. And 1. Now plug in into equation. This 0 will be U dash, negative 2, V dash, W will be 1. So 0, negative 2, negative 2, 0. So if I just multiply them. 1 over 3 multiplied 0. Let me just do it again. It was negative 2. So 1 over 3, 0 minus negative 2. It will be positive 2 over 3. For this one, 1 over 3, negative 2 minus 0, negative 4 minus 0. It will be negative 4 over 3 equals negative 2 over 3 plus 3 over, I have this negative sign over here. So it will be negative, negative, positive 2 over 3. And it will be equal, same. Let me check it if I have done it right or not. So 1 over 3, 0 minus plus 2, 2 over 3, 1 over 3, negative 4. Yes, I guess that's right. So after we apply equations, our value is 2 over 3, negative 4 over 3, 2 over 3, and 1. So I will multiply by 3 to make an integer. 2, negative 4, 2, 3. And close it in a bracket. So that's Miller-Bravas indices that represents that direction over here. So a note to take, if you see, whenever you find the Miller indices for vector which has half length, so it's not full length vector. So if this is vector is a full length in means of z-axis, but this one is a half, we did it and found that answer. But actually this vector, if you try to draw that vector, you will get something like this. You come outside and this one's projection on z-axis will be equal to 1, because this equation gives us a direction where z projection equals to 1, but it doesn't matter because it is not a vector, it's a direction. So this vector is equal to this. What matters for us is the direction, not the length. So that's okay for us. Let's continue. I will not do all of them, but I just want you to take projections for this. Let's just do projection part, A1, A2, and Z. So we are here. How we can go from there to here? Let's see. If I move positive A1, positive A2, and positive 1 on Z-axis. So it's 1, 1, 1. Just plug in the equations and do the rest. Next, for this one, start, end. For A1, A2, Z. So how we can go from here to there? This touches that face over here. If I move full length A1, half length A2, and half length in Z, and all are positive. 1, 0.5, and 0.5, and apply the equations and do the rest. Example 4. A1, A2, and Z. So in order to go there, if I move half length in A1, full length in A2, so 0.1, 1, 0, and that's it. Okay, so here in these examples, in the last examples, I just gave projections because the procedure will be the same. Apply equations, get rid of integers, bring it to integer and enclose in bracket. So here vector was given and we found the Miller-Bravas indices. Now this time we will do the reverse. I have these two directions over here and I need to draw it. So here what we need to do, this is our hexagon. If you see these lines over here, what's required of us is to split each axis into 3 parts. It is 0, So 1 part, 2 part, 3 part. 1, 2, 3, and 1, 2, 3. And I have done for positive side, for negative sides. And I have done the same thing for z-axis. So 1 step, 2 step, 3 step. What we need to do is first open the bracket, -1, +2, +3. So what do I have over here? I am here, and let me change the color. Actually, let me erase this, so we will need this space pen. So now that means it was A1, A2, A3, and Z direction. So I need to move -1 on A1. So I'm here, actually 1, here it's steps, 1 step, 2 steps, 3 step. So here I am moving 1 step in negative direction for A2, -1. I am here, I am moving -1 step in A2 direction. For A3, +2 steps. This is positive side, 2 steps. 1, 2 steps in positive A3, and for Z direction, 3 steps. So 1 step, 2 step, 3 step, and we are here. What's left is connect the dots. Start and so that's our direction that's represented by this indices. Now let's move on to the second one. Let's first open the bracket 2, -4, 2, 3. This one was A1, A2, A3, and Z. If you see, I have drawn some extra dashed lines over here. You will see in short why do I need this one. Because if you see, my steps was 1, 2, 3 steps at maximum, but here I have 4 steps. That means this direction will outflow from the hexagon. So let's see. Here we are at the origin. So here I am at the origin. I need to move +2 steps in A1. +1 and +1 step. Now I am here. Let's wait here. -4 in A2. That's positive A2. I need to move in this direction. So 1 step, 2, 3, 4 steps. Now I am here. I need to move +2 in A3. That's positive direction. 2 steps. 1 and 2 steps. And I am here. And in Z direction, 3 steps. That means 1, 2, and 3 steps. I have drawn some line over here to help me because it's perspective view. It will help me. So 3 steps, it means it will be full length. So 1 step, 2 step, and 3 step. That's end position. Let's connect this line. Start. It will start and end. That's our vector over here. So what do we have? This vector goes to outside of that hexagon. This part stays inside. And if you remember this previous picture over here, this is same. Let's go here. If you see this picture over here, that is this vector. I have got this number 2, -4, 2, 3, and I have drawn it again. 2, -4, 2, 3. So that's it. If you draw this value, you get Z vector, you get direction where Z projection is equal to full length. That's it. Now we are over with directions. We have learned here for hexagonal close packed. So I need to choose some. So what we did do, I can find it. First, the direction was given. We extract the Miller indices value here value in previous slide. Now this time this Miller-Bravatt indices was given and we draw the direction. So let's continue. Here we are moving to crystallographic planes, first in cubes, then I will continue in hexagonal planes, subplanes. If you look at here, I have two cubes stacked above each other. It's the origin. I have three planes, 1, 2, 3. So all these three planes are equal to each other. So because it's infinity, doesn't matter for us. So if you look at its name 0, 0, 1, we use this kind of comma to represent plane, and this kind of we use this kind of bracket for planes and this square bracket for directions. And this is for plane. The students usually confuse these two. But they're here, so we have these planes over here, which are all equal to each other. So if you are given this plane, which is at its origin, what you will require to do to move it up or below to solve it, otherwise you can't. So look at this picture. You have this triangular plane, 3, and this 3 again are equal to each other. So these are plane families. This is called, and it is 1, 1, 0 plane. And also we can this kind of triangular planes over here. So usually when we solve, we will get some values, and that if you try to do that value, you will get something different plane. So what it can be. So imagine this kind of plane over here. This is the same shape but smaller one. Actually, this blue and this planes are equal to each other, so the size doesn't matter. What is left is this plane, actually the big one. Just this part of the plane is inside of that cube. That's why you see that small piece over here. So this plane will be equal to this large plane. So don't get confused. It's the same for others. It's a plane family. Let's continue. These two planes are given. We will try to get Miller indices for that plane. So what's the number that represents this kind of plane? In order to do this, X, Y, Z axis is given. This is origin. Okay. So we need to find intercepts. Intercepts means this kesişme points. So 0, this was 1, 0, 1, 0, 1. Again, the side equals to 1. So at which point this plane intersects x-axis? It will be 1, isn't it? That's our intersection point, 1. For y-axis, this plane intersects y-axis at point 1, and it does not intersect z-axis. This z-axis and this plane is parallel to each other, so intersection will be infinity. The next thing what we need to do is to take reciprocal. It means, so I will do this 1 over 1, 1 over 1, and 1 over infinity. The reciprocal means, let me write it down over here. So it will be still 1, 1, and 1 over infinity will be 0. It is an integer, so you don't need to manipulate. We should have integers. So here it's all integers, so 1, 1, 0. And enclose it in a bracket. That's Miller indices that represents that plane. For this one, this plane, red plane intersects x-axis at 0.5. It does not intersect y-axis. You can say this plane is parallel to y-axis. They never intersect. So it will be infinity. And it also parallel to z-axis over here. It does not intersect z-axis also, infinity. If I reverse them, infinity, it will be 2, 0, 0. it is integers. You don't need to make some processing to make it integer and enclose it in bracket. That is Miller indices for this plane. Let's move on to this one. Here we see some kind of a triangular plane. Let's assume that first this half portion, this full portion, and here let's say 3/4 part is intersected over here. So this plane intersects x-axis at half length. Y intersects at point 1, and for Z, this plane intersects z-axis at 3/4. Take reciprocal, it will 1 over this, 1 over 3/4. It will be 2, 1, 4/3. Now we need to multiply by 3 to make it integer. It will be 6, 3, 4. So enclose it in a bracket. That's it. So let's move on to this. If you look at here, if you have this kind of plane, if you see it goes through the origin, in that case you have to change the origin. And pay attention here, origin was changed to this. That's our new origin. This was the first rule. If a plane goes through origin, change the origin. Now if it is here, let's try to do this now. X, Y, Z. This plane is parallel to x-axis. So it is on x-axis, it means parallel. Infinity. This plane intersects y-axis as -1. This is positive y, negative y. So it intersects y-axis as -1, and this intersects z-axis where? I think it seems a little bit complicated for this one. Let me see. If I choose this point as an origin, x is parallel, y is -1. What about z? It intersects z-axis at 0.5, 1/2. Take reciprocal, will be 0, -1, 2, and I can enclose it in a bracket like this, and that's it. If I try to draw it again, let me see if I did it right or not. So infinity, -1 and 2, actually 0, -1 and 2, reverse it to the infinity, -1, 1/2. If we try to draw this kind of plane, let me do this. I have a number x, y, z. This is the origin. It shouldn't intersect x-axis. It should intersect x-axis as -1. Z-axis at 1/2. Here. Okay, if I just connect the dots, yes, I did it right. Okay. In further slides, I will show you how to draw these planes, which I did here. I just didn't want to check myself, so it was right. So let's see if this plane is given, this Miller indices, how to draw the plane. So first, I will assume that this one is positive y, positive z, and positive x-axis. So open the bracket, 6, 3, 4. Take reciprocal, 1/6, 1/3, 1/4. Now it's time for drawing. For x all are positive, it is 0, 1/6. Let's say it is 1/6 part. Mark the spot. For y-axis, 1/3. Let's say this is 1/3. For z-axis, 1/4. Now mark the points and connect the dots. That is the plane. If you pay attention to this value 6, 3, 4, we have done this one before. This is this one. That's the same, but as you can see, it's some bigger plane. But here, what I did, I found some smaller plane. It doesn't matter, they are the same. We just multiply it by 2 or 3 and 4, you will get the same plane but a little bit bigger size. But for us, it doesn't matter. That's true. Let's look at this one. So open the bracket, 0, negative 1, negative 3. Take reciprocal 1 over 0, 1, 1 over negative 1, 1 over negative 3. So infinity, negative 1, negative 1 over 3. So what I will do here this time, I see that y and z is negative. I will say that this is negative y-axis, negative z-axis, and positive x-axis. I do it so it will be easier to draw the picture. So it should be parallel to x. It should cross y-axis at negative 1, z-axis at negative 1 over 3. And if you saw 0 here, it means your plane will be rectangle. If you see 0, it means rectangular plane. Otherwise, triangle. So here, let's mark the points. For y, negative 1. It should cross over here. For z, negative 1 over 3. Connect the dots. So you should extrude this line so that the plane would be parallel to x. So what I can do is here, I will extrude it like this. Connect the dots. So this plane is 0, negative 1, the negative 0 plane. Does not intersect x-axis, intersects y-axis as negative 1, intersects z-axis at negative 1 over 3. And that's it. Now, hexagonal planes. It is somehow similar. Again, we have 4-axis system. Let's say I have A1, A2, A3, and Z-axis. First, take intersection point. It is 0 and 1. Again, 0, 1, 0, 1. So it intersects, this plane intersects Y, A1 at point 1. It intersects A2 at point 1. You see, this is full length. This is parallel to A2. It intersects Z-axis at point 1, full length. For A3, let's keep A3 empty for now. Take reciprocal, so we are reversing it. 1 over 1, the 1, 1, 1. Let's find A3. A3 is equal to this. Let me write outside negative A1 plus A2. So it will be negative 1 plus 1. So 1, 1, negative 2, 1. And close it in a bracket. That's hexagonal plane. Continue. Let's do this one real quickly. This plane does not intersect A1, A2, and A3. None of it. It will be infinity, infinity. Let's keep this one empty. And intersects Z-axis at half length, 0.5. Takes the reciprocal 1 over 0.5. It will be 0, 0, 2. A3 will be 1 plus A2. But it's still 0, 0, 0, 2. That is the plane. For this one, you see this plane goes through the origin, so I have to move this plane either to this back wall or this front wall. I will choose this front one. Doesn't matter because it is a plane family. This is the correct answer. So this plane intersects A1 as positive 1, A2, A3, and Z. This plane is parallel to A2. It is on A2 axis. It means it's parallel. It's not an intersection. In order to make intersection, it does have to create an angle. So infinity for Z, this plane is parallel to Z axis. Does not create intersection again. So reverse it, it will be 1, 0, 0, and A3 will be negative 1 plus 0. So negative 1, 1, 0, negative 1, 0. That is this plane. For this one, let's write it really quick. A1, A2, A3, Z. For A1, you have this negative side of A1 over here. So this one intersects A1 at -1. It intersects A2 at +1. Keep A3 for now. So it intersects Z axis at point 1. Yes, if you see this point is inclined and it ends at this axis 1. Takes the reverse, it will be the same, and A3 will be negative. Add this together. I don't know if it's -1, 1, 0, 1. That is this plane. For this last one, A1, A2, A3, and Z axis. So this intersects A1 axis at negative side, negative half, 1/2. It intersects A2 at +1. It intersects Z axis at 0.5. If you pay attention, this, let me do this one. This is my plane, and that is Z axis over here. So this plane goes through Z axis. It is 0.5. Reverse it, it will be -2, 1, +2, and A3 will be -2 plus 1, -2, 1, +1, and 2. And close it in a bracket. And that's it. Now, this time let's do the reverse. This time planes are given and we are required to sketch the planes. So what we need to do, open the brackets, 1, -1, 0, 1. It will be A1, A2, A3, and Z axis. So A1. This plane should intersect A1 at point 1, point 1, so 0, 1 again. A2 at -1. Negative, this is positive A2. This side will be negative A2. Here, negative A2. And it should intersect the Z axis at point 1. Here. So what I need to do, connect these dots over here. And you should extend it. If you see this Z axis over here, it should fill the hexagon. So if you just do it like this and connect these dots, sorry, I'll erase it. That is our plane. It starts from this side as it's inclined to this point over here. That's our plane. So let's start to do this one. 1, 1, -2, 0. So open it, 1, 1, -2, 0. So it should intersect A1 at 1, A2 as +1, and this plane should be parallel to 0. If you reverse it, this is infinity. So 1, 1, and infinity, and this will be -half over here. So I will connect A1 and A2. Then I should extend this line so that the plane would be parallel to Z axis. So I will extend it parallel to that. Extend it. And connect this dot also to that. So that's our plane. If you see, this is -A3, and it crosses, intersects A3 at -0.5, which is the case over here. And that's it for today.